Is it working? Okay, hi guys, and welcome to the third Mun lander. And this will be a very special mission. Well, the ship looks pretty much the same, and I only made minor changes in meaning that I fixed the landing legs, and I think I'm going to also change the solar panels with the other ones. Which ones are these? I forgot. Um, but yeah, I made some minor changes. That's not very important. But this episode, I want to do something uh, some experimental stuff. So yeah, I'm going to cut the video because it's going to take too long to explain. But anyway, basically I was showing this game around at school and stuff, and my colleagues were very impressed by it. But then I came around with a small problem, as my teacher pointed out. When I was talking about this game, I was talking about, specific impulse and trust and everything and how it provides data and all that. But there was one big problem that I wasn't, that it didn't have, and that was what what is the mass? I just came around this problem. What is the mass? As you can see around, as I'm pointing around on this little things that we have here. We have a lot of info and details around them, but we don't know exactly the mass. It says 1.25, but basically generic mass units in Kerbania or whatever universe that is. But we don't know what this is. I mean, is it kilograms? Is it tons? Is it no? And I kept having this problem. I said, well, nothing easier to do this but to basically do an experiment and do some basic physics that I learned in school that will help me to find out the mass. So first I'm going to calculate how much mass this thing is, and obviously I'm going to cut this video. I'm only interested in the final portion of the rocket, and I'm going to explain you later why. So just in a second. Alright, here we are back. So after calculating and adding all the mass that is represented here of absolutely all my components, I've come up to the calculation, the sum of the calculation, that this upper part of the vessel weighs pretty much 6.525 generic Kerbal units of mass. And I want to know how much is that in, real life mass. So I said, well, nothing easier. Just I'm going to launch the ship and going to apply this formula, which states like this, that the force or the thrust in case of the ship minus the gravitational acceleration equals mass times acceleration. I'm sorry if I don't say things correctly. I'm not accustomed with the English terms, English scientific terms, but this should be right. But there was a problem that I realized, and that is on Kerbin or whatever it's called, we also have an atmosphere. So that means I forgot to include air friction in this equation. So I said, well, nothing easier. I'm just going to move the entire experiment on the moon and calculate there. And basically what we have is that we will have an acceleration that will be given by this g-force meter. We have the force that is given us by the that is luckily represented as by the uh, thrust over here in kilonewtons. And we also have the gravitational acceleration, which is grandfully given by the double C seismic accelerometer, which is not very precise right now, but hopefully we'll get it. And we also use the time of this experiment to log in the seismic data, which I forgot to do in the last episode, as you remember. Jebediah Kerman, our head scientist, will pretty much be the head mission of this experiment. And let's go ahead and lift off. And I'm obviously going to cut this video because yeah, it's going to take way too long to film this entire procedure of getting to the moon and back, and you know, you've been there. I mean, if you watched my previous episode, you've probably been there and you know what I'm talking about. As you can see, we can see that how much thrust our engine is giving. That is a huge amount of thrust. I need to lower it. You see, up, down, even more. And let me bring out my map and my moon, and of course the ship still, that ship is still there. Can't help it. So I'm going to spare you the time of watching me fail dramatically at the insertion orbit, and I'm going to skip to the part where I actually do the proper experiment, or at least when I'm trying to land on the moon. Okay, so as it might seem, I just lost the recording of the audio, of the microphone audio on this part, but here we are, and we are coming back towards the moon and preparing to land. So, yeah, this is a post-audio recording, and I'm doing quite well, I think. Just trying to slow down so I can land over here safely. A little bit slower. I'm still kind of away from it. 37 meters. I have lots of fuel. I managed to design the ship much better this time, and going to incline it a little bit just to burn and correct my surface velocity a little bit, my lateral one, that means. And again, vertically, and I'm starting to come down towards the moon. I'm ditching the engine and preparing the final part of the engine. Full thrust. As I can see, I took out the webcam this time and I can see the radar altitude going down and down. I want to come down to about 10 meters per second. Oh, and that thing exploded, impacted the ground. Right, 500 meters. We are coming in. Let's burn up. We need to keep it at around 10 meters per second. Whoa, I think I've overburned a little bit there. Not that much, and we're still coming down quite fast. Keep burning, keep thrusting a little bit up. I need to be sure we don't come down too roughly. About 10 meters per second. We're also coming down laterally, less than 100 meters. We're preparing to impact the ground, and whoa! We did hit the ground over there. And that's a little bit odd. We're sliding with our landing legs. Let's just stop and whoop. And there we go. I have to say these landing legs are much better than the previous one. So let's extend our ladder and prepare the scientific experimentation. Let's also transmit this crew report. Wow, look at that antenna. So beautiful. The temperature. And let's see the seismic scan. The sensor has detected a small quake in the surface. Oh, really? Alright, so the toggle display is 0.16 and something G, and that is the gravitational acceleration on the moon, and I think that is about 1.6 meters per second. I'm not very sure, but I know they are modeled realistically. I mean, I know that it has the same gravitational acceleration as the real moon, only that is much smaller, which leaves us with a very dense moon. But yeah, hopefully that is right. So I have this data. I'm now going to prepare my astronaut to get out and get my gather my scientific data. Let's see. Jebediah Kerman, our hero, the small EVA report. Dust is getting everywhere. Let's get back in and transmit this data. And then get back out to take a surface sample and plant a flag in the honor of the mission. Yeah, ladders, as always, not the very best thing. Let's get go. Whoa! Oh wow, we actually landed on our feet. That is so nice. So, let me see. Take surface sample. I said take surface sample. Yeah, the problems of post video recording. The sounds have been really nasty. Impact samples are heavier than normal. Oh yeah, we are actually in the one of the biggest craters on the moon, which yeah, that actually means that was a very nasty impact over there. Nevertheless, that was the surface sample, so let's plant a flag in the honor of the third successful moon landing. So yeah, let's write the third moon landing, whatever, in honor. Let me think about in honor of um or actually let me think this differently. We came here for the mass experiment, so let's write like this: the mass finding, yeah, the mass finding experiment. There we go. That's perfect. Now we're just going to go on our ship, but not before enjoying the low gravity on the moon. Ah, it's so fun. So let's get back in our ship. I wonder if I can jump up to it. No, I think EVA pack. Yeah, EVA pack is the way to go. Oh man, it's quite a little strong gravity over here. Up and grab. There we go. Now let's get back in our capsule. Easily, and I also remembered to do the mystery goo experiment and the materials bay. That's a very valuable science. Fine dust intermixed with we already saw that. So now we're going to go ahead and burn away, and we need to check out our G-force accelerometer because I want to have a pretty much 10 meters per second acceleration to be more fixed, and also I need to check out the thrust of the engine in order to get it right. So yeah, it's going to be, we need to be very careful. That's why I'm going to quick save before I start this. This is the acceleration meters. We need to get it to about 1 g, which means 10 meters per second. We'll need to be very precise and also be careful of the thrust. And I think I'm going to do a quick print screen. Quick save, retract the ladder, and prepare to burn. Any second now. Let's just I want to get this so I'm getting it right. So we are going to burn away and look at our thrust and acceleration at the same time. And we're ready to leave once again and return to Kerbin and yeah, successfully do our scientific experiment. And burning away, we have some acceleration. Let's go full thrust. That is pretty much acceptable. So print screen, and yeah, we are now going to make sure that we go in the good stable orbit around the moon before we do any calculations, because we don't want to crash into the moon. There we go. Very, very easily done. Getting our apoapsis to about 20,000 meters, and then we're going to put a nod and maneuver over there. Let's also retract our gear. And I guess yeah, those broke because we just slide into the moon surface. Should have repaired them, but not such a big issue. So adding a maneuver node. I'm preparing to form our orbit, but I guess you all guys already know this, how this is done. If you watched my videos and if you watch enough videos on Kerbal Space Program, this is pretty much common knowledge. Oh, sorry for not making too many videos. Oh, going ahead a little bit more and burning towards the orbit. Going to start burning a little bit earlier just to get this thing done fast enough and get back to the calculations. I really want to know how much mass in this Kerbal Space Program, and I hope it's something fixed, like I don't know, hundreds of kilograms or tons or something. I don't know. But you may never know. The Kerbal universe is full of surprises. I mean, I think the day on Kerbin is actually 6 hours, if I remember correctly. So yeah, it's obviously going to be different. And this is our perfect insertion orbit, not going to burn anything more. And we're now preparing to return to Earth, so I'm just going to cut the recording again over here and come back when we are close to Kerbin and when we are close to getting the final result. Anyway, see you in a second. So basically the results are in, and I'm going to just take away this part. So basically we will find out how much this weighs, and I'm going to show you how the calculations goes out. So according to the basic physics, how is it called, force laws, or the basic principle of mechanics, I'm not sure how it's called right now. We have the force or the thrust that was lifting us up at that moment, which is 49.5 kilonewtons minus the gravitational acceleration, the attraction of the moon, which in our case will be mass times that g, which is 1.6 meters per second per second. This will be equal to mass times acceleration, which in our case was 10 meters per second per second. So now we just have to replace this with numbers. And we have the kilonewtons, which basically means a lot of thousands of newtons, equals mass times 1.6 equals mass times 10. And let's see, we want to find out the mass. We're going to switch sides. We'll have 5 like this equals mass parentheses, we're going to factorize or whatever that is called in English, and it's going to be 10 plus 1.6. Therefore the mass will be 49500, 49,500 divided by 11.6. So let's just grab really quick our calculator right on the nearby the screen. I don't know if you, I don't think if Fraps is recording it. So 49500. I hope I didn't make any mistakes. I don't think so. Not really that bad at maths. So that basically means 4,267.24 kilograms, because we're doing in international system. So our ship, which in Kerbal units weighs 6.525, in the kilogram mass is 4,267 kilograms. So let's do a simple free basic rule or whatever that is called. So if what was it called, if 6.525 units of mass in Kerbal Space Program means 4267.24 kilograms, that means that 1 unit of mass is equal with x, so that is this little number divided by 6.525, and look at that. So basically 1 Kerbal unit of mass is equal with 653.98 kilograms. So now you have it. Basically each unit of mass in Kerbal Space Program is 653 kilograms, 654 kilograms actually, to be more precise. And now you will be able to make your calculations much more precisely. This thing basically weighs 2 tons. And this thing weighs a lot. A lot. But I guess it's quite accurate. I don't know. If I didn't make any mistakes, I'm going to now edit the video and upload it. So yeah, thanks for watching and see you next time. Bye bye.
Derp, derpity derp 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 derpity derp 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 derpity derp derp
And they're awesome. I'm not
derp derpity derp derp
Prime Minister quarantines Greenland. You know, Greenland expressed extreme concern about the risk of international sin and is shutting down everything to keep people safe.